Okay, let's continue now. You recall that at the end of the last segment, we'd reached as far as observing that in order to proceed with our with computing the terms needed in our weak form, we needed to figure out a way to write out UH comma X, which is sum over A NA comma Xc, Xc comma X, DAE, and the same for WH comma X. Okay, and in particular, the question is, how do we do this term, right? Simply because this one is easy, right? This one is easy, right? We already know how to compute the derivatives with respect to C of the basis functions. Okay, so let's look at how we compute C comma X. And in order to do that, let's just recall that what we've set up for ourselves is a description where omega E, right, and some arbitrary point x in omega E, where xe and xe plus 1 are the nodal positions, right. Some arbitrary point in x is always thought of as being obtained as a mapping from this bi-unit domain. Okay. Now, if we could figure out this mapping, we may have a chance of figuring out what C comma X is. And what we're going to do now is do exactly that. We're going to define this mapping. Okay. So we are going to define the mapping to omega E from omega Xc. It's an extremely straightforward manner in which we're going to do it. Okay, what we're going to do here is the following. We're going to say that any point x parameterized by Xc over element E is obtained by representing it in a basis. Okay, and I'm not going to complete the limits on that summation sign just yet. Okay, we're going to write it as some basis function, right here, and I'm going to leave myself a blank spot for it, times the nodal values. Okay, so we're going to write the nodal values here as a let me think. Okay, so I'm going to write these nodal values as X, E, A. Okay. Now, we're going to have the sum running over the number of nodes in each element, right? So that is A equals 1 to N, N, E. When I write X, A, E, right? What I mean here is for A equals 1, I get X1E and I get X2E. Okay, these are equal to my global nodes X, E and X, E plus 1. Okay. The coordinate x1e is the same as the coordinate xe, right? But when I write xe, I'm viewing that as a global node, right? The coordinate is the same. Likewise, x2e simply is the second node of element E. Well, globally, that is just global node number e plus 1. Okay? All right, because of the fact that we need to write this as a summation over the nodes in each element, and there are, in this case, 2 nodes in each element, which we're writing generally as n sub e. Okay, we need to go to this other sort of numbering for local nodes. Okay, so what I have in the brace brackets here are local nodes, and here the same things appear as global nodes. Okay, those coordinates are the same. It is just that in one case, when we are just viewing a single element, we are regarding those nodes as local nodes, nodes local to that element and numbered 1 and 2 in that element. Okay, when we look at them globally, we recognize that they are one of the many nodes in the global domain, and we number them as xe and xe plus 1. Okay, so just below this, let me also write the local nodes. So that would be x1 for element E, that would be x2 for element E. Okay, so the idea is that we just want to take our nodes, our 2 local nodes, ascribe to them the actual coordinate values, right, that they each possess, and essentially interpolate them. Now, this blank spot that I've left here in the parentheses, right, the parentheses that I've left unfilled is where we're going to put in our basis function in order to do this interpolation of the geometry. Now, we are free to choose whatever basis functions we would want here. It would just mean that we're interpolating the geometry in some way. What is the most straightforward way to do it? The simplest way to do it, one that would probably make our lives the most easy. Yeah, it is to choose the same basis functions as we chose to represent our finite dimensional functions, right? So we just use NA, A being 1 and 2, right? The corresponding to, in fact, the same linear Lagrange polynomials that we already know. Okay, so what we are doing here, using the same basis functions as for representing UH and WH. Okay? When we do this, when we use the same basis functions to represent our finite dimensional functions as well as to interpolate our geometry, we have what is called an isoparametric formulation. Okay? Isoparametric meaning same sort of parametrization. Okay? So we have here an what we have here is an isoparametric formulation. Okay, isoparametric because we're using the same parametrization for our finite dimensional functions as well as for the geometry. Okay, again, it's not necessary, it is just a convenient way to do it. There may be special cases where we don't actually do the same thing, okay, where we don't have an isoparametric formulation. One can design methods of this kind also, right, finite element methods. Okay, but we will be taking the simple approach here, which is to go isoparametric. Okay, all right. What that lets us do then is the following. It lets us say that x comma c is easy to compute, right? X comma c for element E is now sum over A NA comma C X A E. All right, and explicitly this is just N1 comma C X1 for element E, where X1E is the global node number, right? I'm sorry, X1E is the local node, right? But the coordinate X1E is the same as XE viewed globally, okay? Plus N2 comma C X2E. Okay, and just to make that clear, let me state that that is just equal to XE viewed globally. That is just equal to XE plus 1 viewed globally, right? So the coordinates are the same. Okay, again, that's easy enough to do. In this particular case, we know exactly what N1 and N2 are. That's easy to compute. So that is just d dx of N1, which is 1 minus C divided by 2 times X1E plus d dx of 1 plus C divided by 2 X2E. Okay, carrying that out, we basically get X2E minus X1E divided by 2, which is also XE plus 1 minus XE divided by 2. Okay. Now, what we will do is observe that XE plus 1 minus XE for element E is simply the length of that element, right? So we will write this as HE over 2, okay, where okay, this is to be viewed as the element length. Importantly, what this allows us to do from the ground up, even from this very simplest of finite element formulations, is to have elements of unequal lengths, right? So in our partition of the domain omega into subdomains omega E, there was no requirement, and indeed there is no requirement, that the elements all have to be of the same length. Okay, so HE can be different for each omega E. Okay, we don't need a uniform discretization. Okay, so this allows us to have a non-uniform discretization. Okay, and this straight at the very outset, it's an important property of finite element methods. Okay, let's see how all of this works now. So we've done very well. We have gone ahead and observed that, well, where did we start this? Remember, we started this calculation all the way up here. Okay, so what we've seen is that the derivative of x with respect to c, which can be thought of as the tangent of this mapping, right, of the tangent of the map that gives us the physical element from this bi-unit domain. right? Essentially what we figured out is that we found for this mapping, we know that every little we know that the scaling of the element in the physical domain relative to the scaling in the parent domain is essentially HE over 2. Okay, it's a constant because why? Why is it a constant? Because for our geometry, we're using linear interpolations, right? We're using linear basis functions. Okay, that's what makes it a constant. That's what makes this tangent map a constant.